Okay, in the setup of our equation, we need to realize that because we're using a centered finite difference formula, we need at every point or every value of I that we evaluate our function or our equation, we're going to need an I minus 1, t of I minus 1, and we're also going to need a t of I plus 1, which actually means that in this case, we can only evaluate at 4 positions of I, but fortunately, this is also the number of unknowns. So we can evaluate 4 equations in 4 unknowns. Now there's going to be some places where we have known quantities. For example, when we evaluated I equals 1, t0 is known. And so that's going to involve moving the t0 term to the other side of the equation. When we evaluated I equals 4, t5 is known, and that's going to involve moving this term to the other side of the equation. So let me first write things out for arbitrary I. So the equation for arbitrary I, so I'm going to say I1 is less than I is less than n minus 1. So this formulation is going to apply not at 1, not at 4 or n minus 1, but in between. So in this case at 2 and 3, we're going to say ti plus 1 minus 2ti plus ti minus 1 plus h prime ta minus h prime ti equals 0. Okay, so let me make sure that's right. Oh, actually, I multiplied by delta x squared, so I have to actually, let me just add okay, and we also need to collect terms. So here that we've got t sub I in this term and t sub I in that term. And so I feel like multiplying by -1. So we're going to have minus 1 t sub I minus 1 plus 2 plus h prime delta x squared t sub I, and then plus -1 t sub I plus 1, and that is going to equal h prime t a delta x squared. So I'm going to evaluate the numbers here for the particular step size delta x equals 2. But when we actually work on the script, we're not going to assume delta x is equal to 2. But for now, just to illustrate things, if delta x is 2, then this quantity, t sub I squared, is going to be 2.04, and this quantity is going to be 0.8. So this equation, evaluated for arbitrary I, is going to look like -1 t sub I minus 1 plus 2.04 t sub I plus -1 t sub I plus 1 equals 0.8. So this is true. So this equation is true for I equals 2 and 3 in this case, but we have to actually change it a little bit for I equals 1. that's because we know t0. So in the specific case of I equals 1, we're going to have minus t0 plus 2.04 t1 plus negative 1 t2 equals 0.8. In other words, this is actually going to be negative 40. And so what we actually have is 2.04 t1 equals, plus negative 1 t2 equals 40.8. In the case of I equals 4, we're going to have negative 1 t3 plus 2.04 t4 plus negative 1 t5 equals 0.8. This we know to be 200 or minus 200. Therefore, what we have is negative 1 t3 plus 2.04 t4 equals 200.8. So our matrix for a step size of 2 is going to look like the following. Our unknowns are t1, t2, t3, and t4. I find it easier to look at the middle two rows first. So we have 0.8, 0.8, and this is going to be negative 1, 2.04, negative 1, 0. We should follow the same pattern. Usually you just shift things over. And for the first row, going back to I equals 1, over here, we need this equation. So what we're going to have is 2.04 T1 minus T2, and then you don't have these other two temperatures. And then the other side you have 40.8. Okay, the last row involves only T3 and T4, so we're going to have 0, 0, minus 1 times T3, 2.04 times T4, and then 200.8. Okay, so in the last video for this problem, we will actually implement a script that will solve the temperature profile in MATLAB for an arbitrary step size. So for illustrative purpose, we stuck to a step size of 2 so we could have a matrix to write down, but there's no reason we should restrict MATLAB that way. So we'll do the MATLAB script for an arbitrary step size, perhaps starting with a step size of 2.